Let's take a look at another Calc 2 exam. So this is Math 166, Calculus 2, and that just really means we're doing sort of advanced techniques of integration, a little bit more subtler things, integration by parts, trig substitution, trig integration, maybe some numericals as well. This particular exam is from spring 2022. We've got 7 fun problems to look forward to. Let's start with putting our name on, because of course we want to make sure we get the credit. So we'll put down that we're going to do the answers, because that's what we're after, is the answers. And let's get going. Number 1, evaluate the integral 3 secant to the 4th power of 5x dx. Now the 5x, that's just there mostly for distraction. That won't really do anything. Our key to look at is the fact that we have an integral only involving secant. So this falls into the secant tangent category of integration. And in that category, there's one of 2 things you want to do. Well, you either want to get everything in terms of tangent times the secant squared, or everything in terms of secant times the secant tangent. If you're not in one of those, watch out, secant cubed. Don't want to fall into that hole. So again, we'll just go ahead and write it out. We want tangent stuff, and then a secant squared on the end, or we want secant stuff and a secant tangent on the end. So that's what we're after, one of these 2. And so we say, okay, which one seems easier to do? Well, we don't see any tangents at all, but we see a lot of secants. So we're thinking, all right, we're going to put ourselves into the secant squared category. So what do? Well, we're going to pull off a secant squared and say, all right, we're going to use that, and then we have to deal with the rest of the stuff. So we say, all right, so we really have 3 secant squared of 5x and secant squared of 5x dx. And this part on the end will become our du in essence. Well, so what is left for us to do is to somehow say, how do we rewrite this first part just in terms of tangent? Now, for this, no surprise, we have a lovely trig identity. And it says the following: tangent squared plus 1 is equal to secant squared. Which is another way of saying, essentially, if you have a tangent squared, you have a secant squared, and vice versa. So we say, oh, well, what we can do is you can replace the secant squared with the tangent squared. And so this is the same as the integral of 3 tangent squared of 5x plus 1, parenthesis, and then secant squared of 5x dx. And notice we're in the right form. Tangent stuff with a single secant squared on the end. Perfect. Perfect. Just what we want. So now, once we're in our right form, we're almost done. We make a quick substitution. So u would be tangent of 5x. Then our du, well, is derivative tangent is secant squared. That's why we wanted to get there. But be careful. Chain rule, we're not going to forget it, says you throw a 5 out in the front. Well, using our advanced technology, we can say, well, that's really the same as 1/5 du equals secant squared 5x. So what we now have, well, we have the 3, we have a u squared plus 1, and we have a 1/5 du. All right, well, all right, so that's 3/5, and the integral of u squared is 1/3 u cubed. The integral of 1 is u, and of course we can put on a plus c. And if you wanted to, you could even distribute here. And so what do we have? Well, 1/3 and 3/5 multiplied together gives us 1/5 u cubed, but u is tangent, so that'd be tangent cubed of 5x. Then we have 3/5 of just the normal u, tangent of 5x, And then, of course, because we don't want to lose any points, and we're always careful, we make sure to put a plus c and done. That's it. That's it. That's the whole thing. So this is what we'd call a trig integration, which relies on rewriting the integral into something that's more easy to handle. They basically fall into two camps. There's the secant tangent camp and the sine cosine camp. And so in the secant tangent camp, it's a little bit more subtle. You have to remember, I either want secant squared on the end with tangents or secant tangent on the end with secants. But once you know where to go and you remember the right trig identity, these problems tend to work themselves. So this is just a plug. Know your trig identities. And the better you know them, the farther you'll go. So, well, one down. Let's keep going. Number 2. Evaluate the integral of 2x cubed e to the x squared dx. Okay. Now, right at the start, this looks like some sort of integration by parts, because we see multiplication, the x cubed and the e to the x squared multiplying together. Well, there's a little thing, of course. There's some subtlety. E to the x squared is actually hard to integrate. It's one of the things that we really can't integrate with our standard functions. So what do we do? Well, one of the things that we should do is we should always fall back on the mantra, let's do something simple before we do something more complex. And the simplest thing to do, and oftentimes the best go-to, is substitution. The goal of substitution is to rewrite things to make them easier to see what's going on. And so for us, we say, well, it would be easier if we could see what's happening with this e to the x squared if it was just like e to the something. So let's make a substitution. So we say, all right, let's let u equal x squared, and then we'll let du, that would be 2x dx, and of course the reason it's x squared is that's on the inside, and substitution is an inside job. Okay. So, looking at this, we say, well, what does this integral look like? Well, there's a 2x here, but there's actually 2x cubed, so we can write this as x squared e to the x squared times 2x dx, right? Because I pulled 2x off on the end. Then we say, oh, that becomes u e to the u du. Already, that feels like a much easier integration. And this is also more clearly integration by parts. So we're like, cool, woohoo! Now, here's the thing. I like to do integration by parts by u dv. But that's not really good here because it's easy to get confused. So let's just go ahead. There's this old trick called, if it's going to confuse you, change the letters. So let's change, say, these u's to t's. So t e to the t dt. So this, I'm just going to relabel the variable because I'm an old person. You're a young person, or at least you're young at heart. And so if you don't need to do that, don't worry about that. And so now I say, okay, I have my two pieces. I say, well, what can I do? I want one to differentiate. I want one to integrate. And I say, well, all right, the e to the t doesn't matter if I integrate or differentiate. It's going to be e to the t. The t, well, I want to differentiate that because that makes it simpler. And the goal is always to make things simpler. So I say, okay, so we should let u equal t, and then du would be dt, and then v will be the rest, e to the t dt. Oops, dv is e to the t dt, and v is e to the t. So this would become our uv t e to the t minus our integral of v du. So minus integral of e to the t. All right, so that's t e to the t minus e to the t, of course, plus c. But now we sort of work our way back, and when we said relabel our variable, so we said u, which was x squared, has now become t. Say, okay, so t was what? Well, it's what we called u for a moment. Of course, then we called u something else. But then we say, well, it really, in terms of the original, represents x squared. So this becomes x squared e to the x squared subtract e to the x squared plus c. And we've successfully found our integral. And there we go. A nice integration by parts problem. And do you need to do the substitution at the start? No. But it kind of helps clarify what's going on. And I like clarity. I like understanding what's going on. And so it's a good strategy. One of the ways I like to think about problems is I like to think of it as it's just a layer after layer of simplifying. You start with something that looks really complex, chip away, make it less complex, chip away, make it less complex. And if you chip away enough, what's left is the answer. And so don't think of it like, I got to do everything everywhere all at once. No, 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 no. Just do just enough, and you'll be great. All right, well, 2 down. Let's keep going. Number 3, evaluate the integral of 2 to the power 6 x squared square root 1 minus 4x squared dx. Now, 2 to the 6, normally we'd just put 64, but not everybody knows that 64 is 2 to the 6th power, and I suspect what's going to happen is there's going to be a lot of 2's along the way. And so, well, we'll see what happens as we go along. Now, what kind of problem are we in? Well, when we see a square root, especially on this type of exam, in the back of our heads, it's like, uh-oh, is this trig sub? Well, wait, I didn't mean to say uh-oh. I said, woo, yeah, is this trig sub? Okay, so we're thinking trig substitution. So, all right, so is it? Well, we take a look at the form. And what we're looking for in trig substitution is like number squared plus variable squared, or number squared minus variable squared, or maybe variable squared minus number squared. So there's sort of 3 different categories. So one category, we'll just refresh ourselves, is if we have variable squared plus number squared, okay, well, that says you should go with a good tangent substitution. If we have ourselves variable squared minus number squared, well, that says we should go with a secant substitution. And if we have number squared minus a variable squared, we say, that case, we should go with a sine. All right. Now, where are we? Well, again, you oftentimes look into your square root. We say, well, what do we have? We have ourselves 1 squared minus, and I'm going to think of this as 2x squared. They say, number squared minus variable squared. What's our substitution? So our substitution says, okay, we should let our u, which is 2x, should be sine of theta. All right, so now let's start working through and see what happens. Well, this gets a couple of things, right? We start taking derivatives. 2 dx is cosine theta, d theta. All right, that's good to know. What else? Well, what about the square root of 1 minus 4x squared? And, well, the square root of 1 minus 2x quantity squared, that's the square root 1 minus sine squared. And this is, of course, the whole thing. Why do we even try this? Why are we bothering? Well, 1 minus sine squared is cosine squared. Say, well, that's nice. It's the square root of a square. That just becomes cosine. Isn't that lovely? All right. So we say, all right, what do we have? We start piecing things together. So we're going to replace a 2x by a sine. So let's think about what we have here. Let's see. Here I have an x squared, so I want to make that a 2x squared. We're going to borrow some 2's from that 2 to the 6. The square root of 1 minus 4x squared, okay, we're fine with that as is. We know what to do with that. And then I want to have a 2 dx, a 2 dx on the end. Not just a dx, a 2 dx. So I say, how many 2's have we borrowed so far? We've borrowed 1, 2, 3. we have 2 to the 6, which means we have 2 cubed left. So we're going to have 2 cubed. Now, well, here we have 2x squared becomes sine squared. Square root of 1 minus 4x squared becomes cosine. 2 dx becomes another cosine. So, all right. So we have a 2 cubed sine squared cosine theta cosine theta. Or if you look and say, well, we have sine squared cosine squared. Now, say, oh, what is that? Well, we actually say, oh, we kind of like have 2 sine cosine. You know, we go back to our trig identities. This is now a trig integral, and essentially we're into power reduction mode. Say, ah, this is the same as, I'm going to have a single 2, and then I'll think of it as 2 sine theta cosine theta squared d theta. Well, that is sine squared. No, we'll go ahead and write it this way. Sine of 2 theta quantity squared. Right? Because 2 sine theta cosine theta is sine 2 theta. Well, all right. How do we rewrite that? Well, Again, we go back to our trig identities. Power reduction. Sine squared. What can we do there? Well, it's the same as 1 minus cosine of twice our angle. Now this is got to be really cautious here. You say twice our angle, 2 theta, right? Well, no, it's twice what we start with. We already start with 2 theta. So twice 2 theta makes 4 theta. And divide that by 2. Like, ah, cool. The 2's cancel. And so we at this stage have integral of 1 minus cosine of 4 theta d theta. Life is good. All right, let's move this up. And so what's the integral turn out to be? Well, that's not bad. We can integrate these things, so that's theta minus integral of cosine is sine. And then, of course, we have to compensate for the 4, so we do that by 1/4. All right. Good. Are we done? No. What do we have to do? Well, we have to unravel. Now, there's a couple of ways to unravel. So we'll follow the unraveling trick that the solution's posted here. Depends on how you're feeling. But really, our goal is to say, well, look, when we talked about where we started, we talked in terms of sines and cosines. So we have to get back in terms of sines and cosines to figure out where our final answer looks like. All right. So let's switch gears now. We've got this lovely space here. And we say, all right, we know a couple of things. We know 2x equals sine of theta. Well, that's the same as saying theta is arc sine of 2x. So we know how to handle the theta part. Now the sine for theta, well, we got to do some unraveling. So say, okay, 1/4 sine of 4 theta. Well, I can think of sine of 4 theta as sine of 2 times 2 theta. So this is 1/4 times 2 sine of 2 theta cosine of 2 theta. Okay. Well, sine of 2 theta, we can do something with that. So that's 2 sine theta cosine theta. So that's just the sine 2 theta, 2 sine theta cosine theta. Now cosine 2 theta, there's actually lots of different trig identities. There's cosine squared minus sine squared, but that's the same as 2 times cosine squared minus 1, which is also the same as 1 minus 2 sine squared theta. So that's a trig identity, double angled for cosine 2 theta. And all right, so the 1/4, the 2, and the 2. all cancel. That's very convenient. And I don't know if this is actually helpful or not, but well, it's too late now. I'm fully committed. So we have sine of theta, which is, and pull it back down, sine of theta is 2x. So this is going to be 2x. Cosine theta, we actually can see it right here. That's our square root, 1 minus 4x squared. And then we have 1 minus 2. And then sine, well, we go back, say, hey, sine is still 2x. So 1 minus 2 times 2x, that's squared. And so, all right, so 2x square root 1 minus 4x squared times 1 minus, and this will be 2 times 4x squared, which is 1 minus 8x squared. All right, so we know how to handle the theta. We know how to handle 1/4 sine 4 theta. So we put them together. And we end up with an answer, arcsine of 2x minus 2x square root 1 minus 4x squared times 1 minus 8x squared plus c. And that's our final answer. Ah, whew. Good. Done. Done. Now I will say that from a personal perspective, it just depends on how much you want to tolerate things. But let's suppose we were like, well, I just want to know an answer. We could have said something else here. We could have said, well, look, we know what theta is. It's arcsine of 2x, yeah? Well, yeah. So this could also have been arcsine of 2x minus 1/4 sine of 4 arcsine of 2x plus c. And technically this is also correct. And but of course that's not what they want. They want you to sort of unravel at the end. It's, you know, what are you in the mood for? Try to make your graders happy. Try to have it be what they're looking for. So that's what I recommend. All right. Well, whew, this one was a bit of a workout. We had trig sub, all sorts of substitutions, keeping track of our powers of 2 and making sure they were just right. And you could see that they carefully planned it so that by the time you got to the actual integration, all your 2's had been used up. And so that you had something which was pretty straightforward to integrate. All right, well, a fun problem. And I hope you have a fun problem too on your test. You know, that's, you know, we should always be lucky enough to have fun problems. Okay, let's go on to the next one. Number 4. Find the integral of x plus 1 divided by x minus 1 times x squared plus 1 dx. Now this one is basically telegraphing exactly what it wants us to do. Have polynomial on top, polynomial on the bottom, rational function. This is definitely partial fractions. And so we're just going to go right for it, partial fractions. And so we say, all right, what's the procedure? Well, the procedure is, most of it is algebra. The majority of this integral is not an integral. The majority of it is algebra to rewrite things. But that's what most of integration is. The majority of integration is just saying, well, there's like 10 things I can integrate. What can I do to make what my current integral is look like one of those 10 things? And so partial fractions is just one such technique. So the way we begin is to say, well, we have to understand how to pull this apart. And we look downstairs. Say, all right, we see an x minus 1 and an x squared plus 1 term. We don't need to do long division. It's always good to double check. We don't need to do it because the degree on the top is 1. The degree on the bottom is 3. So lower degree on top means no long division. So the next thing is to say, well, we're going to have the first piece, x minus 1, and then we're going to have the second piece, x squared plus 1. And we say, well, what goes over the x minus 1 is some number a. What goes over the x squared plus 1? Well, bx plus c. Now, why bx plus c here, and just a there? It's the fact that x squared plus 1, the technical term is irreducible quadratic. Can't factor any further. And so we have to have that there to account for such a situation. And the goal is, what are A, B, and C? It's not that this is true for an arbitrary A, B, and C, but importantly, it's true for some very special choice of A, B, C. And so our work is to say, what's the right A, B, C? What's the one that's super special? So at this point we say, well, okay, let's clear out our denominators. And so we're going to multiply both sides of the equation by x minus 1 times x squared plus 1. So we end up with x plus 1, we've cleared everything out there, is equal to a. Here, the x minus 1's cancel, so that's multiplied by x squared plus 1, and then plus bx plus c. Here, the x squared plus 1's cancel, so it's multiplied by x minus 1. And we start saying, well, let's make good choices. What's a good choice? A good choice is anything where we get cancellation. So x equals 1, that's a good choice. And if we do that, we'll see, well, we get 2 is equal to a times 1 plus 1, which is 2a, plus b plus c times 0. 0, that's great. That's why we chose 1. So we say, aha, a is 1. And now this one you're like, well, anything good left? There is actually something good. You see that x? I can choose the cancellation to knock that out. That's 0. So if we do x equals 0, we get 1 is equal to a. But wait, we know what a is. A is 1. So 1 plus, and then here, what do we have? We'll have 0 plus c, which is c, times 0 minus 1, which is negative 1. All right, well, what does that say? 1 equals 1 minus c. That says c is 0. Okay, great. Now we know a and we know c. Okay, anything else? Well, not really. Not anything good to knock stuff out. But that's okay. We already know 2 out of the 3. We're in good shape. So what we can do is we can just pick another convenient number, or inconvenient, doesn't really matter, it doesn't have to be convenient or inconvenient. How about negative 1? Why not? Negative 1 plus 1 is 0. We get a times 1 plus 1. Well, that's 2a, but we know 2a is 1. Sorry, that's 2a. We know a is 1, so that would be 2. I have to be careful there. So that's 2. And then plus, we're going to get b times minus 1 plus 0. So we're going to get minus b. And then minus 1 is minus 2. So what does this say? Well, this says that 2 plus 2b equals 0. So what is b? So b has to be negative 1. All right, good. So now we know a, b, and c. And so the punchline is the following. Our original integral, which is x plus 1 over x minus 1, x squared plus 1, becomes the integral. Well, we're going to have a over x minus 1, so 1 over x minus 1, and then bx plus c. Well, that's minus x plus 0. So that'll become minus x over x squared plus 1. And we're in a better shape. Because we've pulled things apart into smaller pieces, smaller, easier to digest pieces. And the first integral, okay, that's no surprise. The second integral, it almost looks like something that works great with logs, right? Because if you set u equal x squared plus 1, du would be 2x dx. So we can say, oh, well, imagine I put a 2 upstairs and a 1/2 out in front. Then we say, perfect, right? So what do we have? The first part would be log x minus 1. And then the second part, we see x squared plus 1 downstairs, 2x upstairs. And so whenever you see function downstairs, derivative upstairs, that's the natural log of the downstairs. So minus a half natural log x squared plus 1, and of course, plus c. Don't forget that, important. And there we are. There it is. There's the integral. We found it. Woohoo! Nice. I have to say I'm a little sad that there's no arctangent, but that's okay. Maybe we're saving that for another problem. Who knows? There's still more problems to do, right? We still have 3 more chances to get an arctangent. Fingers crossed. Number 5. Find the volume which results from rotation, the region. I think they missed a word here. Maybe rotation of the region or rotating the region. All right, rotation of the region. X goes from 4 to 5, so there we have that. And y goes from 0 up to this curve. So, they actually even drew us a picture. Square root 5x minus 12 over x squared minus 5x plus 6. And around the x-axis. Wow, we didn't even have to draw anything. They did it for us. How lovely. Now, we have to think about, well, what's the right technique? What's being used here? Well, we look at this and say, all right, we would think about this in terms of slicing. So we'd take a small slice. We're going to integrate with respect to x, because everything's in terms of x. And so when we spin this, what we see, we say, oh, this forms a disk. So this is a problem that connects back to the disk method. Okay, so how do you find volume? So the volume would be, for a disk, it's integral a to b pi, then it's your radius squared, and your thickness. So remember, this isn't a washer, this is a solid disk. So if it was washer, we'd have outer radius squared, subtract inner radius squared. Here it's just radius. Okay. So in our case, we'd say, well, that's the integral for up to 5, our bounds, pi, and the radius, it's the height. It's this thing. Well, it's the square root, and once we square it, well, that makes things a little bit easier to see what's going on. 5x minus 12 over x squared minus 5x plus 6. And the thickness is the dx. All right. Now pi, that's just a constant. And so what we're really asked to do is we're asked to integrate 5x minus 12 over x squared minus 5x plus 6. Well, what's that? It is partial fractions again. Just when you thought like, it's safe to go back in the water, another partial fractions emerges. Well, we'll make some comments here. X squared minus 5x plus 6, does it factor? Yes. And of course, if you're doing partial fractions, you should expect things to generally factor pretty well. You need 2 things that multiply to 6, add to negative 5, and I claim it's x minus 2, x minus 3. You can check, you get x squared minus 3x minus 2x is minus 5x, and plus 6. So we digress for a moment. 5x minus 12 over x minus 2, x minus 3. It should look like something to be determined over x minus 2 plus another something to be determined over x minus 3. Clear your denominators, and so that means multiply everything by x minus 2 times x minus 3. We'll get 5x minus 12 is a times x minus 3 plus b times x minus 2. And good choices. Make good choices. You feel like, it's your parents talking to you when you're heading off to kindergarten. Make good choices. Make good choices. And so in our case, well, things that knock out terms. So, for instance, if we choose x equals 2, 10 minus 12 is negative 2. And we get a times 2 minus 3, which is negative a. So that says, a should be 2. If we choose x equals 3, we're going to get 15 minus 12 is 3 equals b. And notice that, of course, we didn't say it out loud. When you plug in x equals 2, that goes away. When you plug in x equals 3, that goes away. And so they say, great. So b is equal to 3. So rejoining our integral in progress. It is pi, go ahead and pull that out, 4 to 5, and then we have 2 over x minus 2, and then plus 3 over x minus 3. And we have to integrate that dx. Well, that's not a bad integral. So we get pi, we'll get 2 log x minus 2 plus 3 log x minus 3, evaluated from 4 to 5. So we're in the home stretch. We got to places. Each of these pieces is easy to integrate, so we integrated. Not surprising, log shows up a lot when you're doing partial fractions, so much so that you kind of anticipate logs are coming. So the last part, of course, is just evaluation and cleaning up. And of course, we want to make sure not to lose any points. So we'll go through carefully. And what do we have? So we have pi, plug in the top value, 5. 5 minus 2 will give us a 3. Now we'll have 3 log 5 minus 3 gives us a 2. Subtract 2 log, and well, we have 4 minus 2 is a 2, and 3 log 4 minus 3 is a 1. Okay, we can simplify. 3 log 1 is 0. Okay, so that term is gone. Log of 1 is 0. Whoops, sorry about that. There we go. And all right, we can certainly combine these two pieces together. So we have here, we have pi, we have 2 natural log of 3. 3 log 2 minus 2 log 2 is plus a natural log of 2. And if we wanted to, we can even put these together, right? Because this 2 comes in as an exponent. So that's log of 9 plus log of 2. So we could say, oh, this is the same as pi log of 18. Where did that 18 come from? 3 squared times 2. And there we go. An answer, a lovely answer. Very compact. And you might say, well, could we have stopped here? Yeah, because it didn't say simplify as much as possible. So stop where you're comfortable with, unless, of course, it says simplify. And usually if it says simplify, something nice does happen. All right, a nice application, deja vu, a callback to our first exam. And applications are good. We'll probably see those on the final as well. But now, that means we just have 2 problems left. Well, okay, let's go do those. Number 6. A large tank is being filled with water. Now, due to changes in the water pressure, the water is entering the tank at different rates. A table of values of the rate of water flow given in gallons per minute at 3-minute intervals is provided. So that's very nice. We have 3-minute intervals and the rate of flow. Oh, that's weird. There's an A here. I wonder what that means. Probably means 8 gallons per minute. Well, let's see what part A has to say. If the trapezoidal rule is used with n equals 4 to approximate the total volume of water in the tank after 12 minutes, there are approximately 60 gallons of water in the tank. Find the rate of water flow A at time t equals 9 minutes. Oh, okay. So it says we're using the trapezoidal rule. And all right, well, first off, it says n equals 4. And so what does that mean? Well, it says you're taking your interval from 0 up to 12, and you're breaking it up into 4 equal pieces, which, well, almost as if it was meant to be exactly the pieces that we have. Now, how does the trapezoidal rule work? Well, I like to think of it as the 1, 2, 2, 2, 2, 1 method. And so, in other words, we give the weights on the end slightly less than the ones in the middle. And so we have the following. We would say that our approximation 60 is equal to, So the trapezoid rule, you have your width, and in our case, our widths are 3. So 3, and then you have a 1/2, and the reason that you have a half here is because of these 2's there. And then we have the following. Well, we're going to take 1 times what's happening at time 0, which is 5. 2, what happens at time 6. Sorry, what happens at time 3, which is 6. 2 times what happens at time 6, which is 7. 2, what happens at time 9, which is A. And then 1, what happens at time 12, which is 3. All right. Well, we start to unravel. Now, I can move the 3 across, and I can move the half across. I divide by 3, multiply by 2. That would say 40 is equal to, and here we have 5 plus 12 plus 14 plus 2a plus 3. All right, 5 plus 12 plus 3 would be 20, plus 14 would make that 34. So 34 plus 2a. So what does that say about a? Well, subtract 34, and then we have 6 equals 2a, so a equals 3. Now we pause and say, does that seem right? So if we had gotten an answer like a is 50, we say, that's not fitting in with the flows here. If we got an answer saying, oh, a is 0.001, that's not fitting either. You kind of say, I kind of want it to be something like these numbers, and 3 is definitely like those numbers. And so we say, aha, that's our answer. That's good, it's very reasonable, and we figured it out, right? So we set up our approximation from the trapezoid rule equals the formula you get from applying the trapezoid rule, and then you figure out what a has to be. A is 3. Okay, well that actually wasn't so bad. And then it says, okay, part B. Now, let's not use the trapezoid rule, let's use Simpson's rule. Now, Simpson's rule is a little bit curious. So it goes 1, 4, 2, 4, 1 in our case. Normally it alternates 4, 2, 4, 2, 4, 2, 4, and then ends with 1. But we just have a few data points. And so the key is to remember, like, well, we're weighting things slightly differently. So it's like every other term gets slightly more weight. And so, okay, so what happens here? We get the following. We're going to have our Simpson's rule. Where we'll have our width again. That's always there, 3. And then there's a factor of 1/3. So this 1/2, this is for the trapezoid rule. And this 1/3 is for the Simpson's rule. And the reason that we have these is because of the weighting here. You see, because of these factors of 2, we have to compensate. And if you think about it, if we alternate 4 and 2, 4, 2, 4, 2, well, on average, it's like we're taking it multiplying by 3. So that's where we have a 1/3. And now we go through, we'll update our table here. And so we're going to take 1 times what happens at time 0, which is 5, plus 4 times what happens at time 3, which is 6. 2, what happens at time 6, which is 7. 4, what happens at time 9, which is now 3, thanks to what we just did. And 1, what happens at time 12, which is also 3. Well, 3 and 1/3, that's simple. They just cancel. So what do we have? Well, here we'll mark that really quick. So we just make sure we know what goes on. And so what we have is we have 5 plus 24 plus 14 plus 12 plus 3. So let's see. Well, if we added these two together, that would be 38. And then here, we added those, that would get us up to 50. And then we have 5 and 3 more. That makes it a grand total of 58. And so our estimate, we can even say what it is, 58 gallons is our estimate using Simpson's rule. Now again, Simpson's rule and trapezoid rule shouldn't be too far off because they're both estimating the same quantity. So we saw 60 was the estimate for trapezoid. If we got 1,000,000 for Simpson's, we'd be highly suspicious. Or if we got 4, we'd be highly suspicious. But we're near 60, so we're like, yeah, we should be close. They're both estimating the same quantity. They should both be in the same ballpark. So 58, a beautiful answer, and we're done. That's it, right? And of course, the key to remember is how the rules work. The patterns, 1, 2, 2, 2, 2, 2, 2, 1, are 1, 4, 2, 4, 2, 4, 2, 4, 2, 4, 1. And once you remember that, most of it just sort of follows along. So, wow, that was number 6. That means we only have one problem left. Our last problem, number 7. Find the indefinite integral in part A, and then evaluate the improper integral in part B. All right, so we'll do part A first, because it says do that first. We are asked to find the integral of e to the x over 1 plus e to the 2x dx. Now, there's something that they like to do here, and let's just point out what it is. The e to the 2x is cleverly hiding something. What is it hiding? Well, this is the same as e to the x quantity squared. Now you might say, well, wait, Steve, I can play this game too. It's the same as e to the 2 to the power x, right? Yeah, but that's not useful, so we don't do that. But why is e to the x squared helpful? Well, because we have an e to the x upstairs. Like, ooh! So we can convert e to the 2x into e to the x, so we have sort of an apples to apples comparison. And so that makes it easier for us to work with it. So we say, all right, so really this is the integral of e to the x over 1 plus e to the x squared dx. And we say, well, that's obvious substitution. We'll let u equal e to the x. And then du is e to the x dx. And of course, when we say u equals e to the x, what we're really setting ourselves up for is that this e to the x upstairs is going to become our du. So what do we have left? Well, we have the integral of du over 1 plus u squared. Okay, well, that's not too bad. That is, it happened! It's finally happening! It's arctangent of u. Woohoo! Yes! I knew if I was a good math student that it would show up, and it did. Okay, but we're not done yet because arctangent of u, well, u is not x, right? So we got to substitute back, and arctangent of e to the x plus c. And there we go. A beautiful, beautiful answer. All right, and don't forget you need the plus c here. It is an indefinite integral. So this is, I keep saying that, but I know these graders, they take points off if you forget those. We're not going to do that. We're going to get all the points. That's our goal. Got to get them all. Got to get them all. Okay, so now this is an improper integral. What makes it improper? Is there any division by 0? No. There's no vertical asymptotes. But there is an infinity involved. So we'd say, well, this is really the limit as the upper bound goes to infinity of the integral 0 to b of e to the x over 1 plus e to the 2x dx. So that's how we'd handle it. Well, we can actually integrate that because that was the whole moral of part A. So this is our limit as b goes to infinity of, well, arctangent e to the x. We don't need the plus c anymore because it's a definite integral now. Evaluate that from 0 to b. And, well, that's the limit as b goes to infinity of arctangent e to the b, subtract, and then we're going to have arctangent of e to the 0, which is 1. All right, so, good. This is a chance we really get to dig into arctangent now. So what does arctangent do? Well, if you remember where arctangent comes from, it's the inverse function of tangent. And so what you do is you take the tangent function, and that has vertical asymptotes at pi over 2 and at negative pi over 2. And those vertical asymptotes become horizontal asymptotes. And so arctangent does the following. It will go and do that. So that's one piece of the tangent function just turned sideways. So what's happening here? So this arctangent e to the b, the inside is getting big, and so we're going further to the right, and so we're going to have that this approaches the asymptote, which is pi over 2. Arctangent of 1, well, what tangent of what gives you 1? The answer is pi over 4. Of course, it doesn't just go to pi over 4, it's always pi over 4. So what we see is that, oh, okay, so our answer is in the limit, it's pi over 2 subtract pi over 4, and that would be a pi over 4. Done. Wonderful. What a great way to finish the test. I was glad we stuck it out to the very end so that we can get to that arctangent. It just brings you joy. It brings you joy. I have tears coming to my eyes. Just what a fun problem. All right. Okay. Well, thanks for sticking it out with me, and I hope you do well. I really believe in you. I know you can do this. You have the capability. You're amazing. Use your skills and just be yourself. Be great. And until the next test, we'll see you later. Bye.